Okay, next topic is the second derivative test. So we've already covered the first derivative test to find local extrema. That's what this question's asking us, to find local extrema. We did the first derivative test last time. And the little visual summary of that is you put your CPs on an F prime line, and then you're just checking for sign changes. Because this went from increasing to decreasing, local max. Because there was no sign change, just a CP. We're going to add, this time, the second derivative test is just an alternative to that. You can do the first derivative test, or you can do this new second derivative test, just another way to find local extrema. And so I put this example because I want us to practice the quotient rule to find the derivative, because local extrema occur at CPs. CPs happen when your derivative is 0. So we have to get the derivative, and then we'll set it to 0. We'll find the values of x that make that true, and then we'll check, this time, with the second derivative test to see which of those CPs are max, which are min, which are neither. Okay, so this function has a fraction. We'll come back later and show that there's another way to do it without using the quotient rule. But just by means of practicing, we see the fraction, let's go ahead and do the quotient rule. So the quotient rule has this particular structure. Denominator times derivative of the numerator minus the numerator times derivative of the denominator, all over the denominator squared. Okay, so fill in the boxes where you're just copying. The derivative of x squared plus 9, the numerator, goes there, and that's 2x. The derivative of the denominator is 1, that goes back there. And then we want to simplify, oh, I gotta square this, right? I want to simplify the numerator, so I'll have a 2x squared minus x squared minus 9 all over x squared equals 0. That's the equation I'm trying to solve, so I can find the values of x that make that a true statement. And I can clean things up in the numerator a little bit. That's x squared minus 9 divided by x squared equals 0. This is a fractional equation, and we know from the pretest the only time a fraction can be 0 is when our numerator is 0. So we focus on that. And now we just have to solve this quadratic equation, which does factor in x plus 3x minus 3. Or you might see right away, you can just see that there's 3 plus 3 and minus 3 are the roots. Oops. So we got 2 CPs for this problem. Again, we could come back and do the F prime line, and that'd be a good thing to check, just to check your work later. But we're going to now talk about using the second derivative test. And so we're going to look at each of these and say, what does the second derivative tell us about the CP at x equals 3? And let's see, maybe I will put our derivative is summarized. I'll put it up here. Make some room. And we found the 2 CPs, x equals 3 and x equal minus 3. Okay, so we're going to take a second derivative and then use the information in the second derivative to tell us which of these CPs might be a max and which might be a min and which might be neither. And so I'm going to take the second derivative, and I can do another quotient rule, but just to show you the algebraic simplification that also might have helped us up here. I can take this and divide this way, right? I can split that fraction into like 2 separate fractions. The reason I might want to do that is x squared over x squared is just 1, and this is 9x to the minus 2. So rather than looking at it this way as this is still f prime, right? I haven't taken a derivative. But rather than looking at it this way, I've massaged it down into this form, which is a whole lot easier to take the derivative of. Now again, this might be a good thing to practice on your own time. You could have done the same trick all the way up here, and it would have made it much easier. To take that derivative. So down here we have this as our our first derivative, and we want to take a second derivative of this. And so we'll go times the power down a power. Okay, now what do we do with that for the second derivative test? What you're going to do on the second derivative test is take each CP and plug it into the second derivative. And then you're going to decide if that was greater than 0. What that means is that the function is concave up at that critical point. You have a horizontal tangent line, and then your function's concave up there. So what can you conclude about that CP? It must be a local min, right? Because it was concave up. So just think about the picture. Concave up implies there's a local min. So we're going to try that for 3. We're going to try that for -3. What happens at the CP you plug in and you get a negative value? Well, that tells you your function is concave down at that CP. So your point has a horizontal tangent line, and then it is concave down. The function goes like this. So it must be a local max there. So nothing to memorize if you just think visually and understand this. Or if you're a person that likes to make a study guide, like make this your step for the second derivative test. That's a good summary of the second derivative test. And again, nothing to really memorize if you just say, oh, greater than 0 means what? Oh, that's concave up. Okay, so therefore it must look like this, local min. Okay, so we plug 3 and -3 in. When we plug 3 in, we see we have a positive over positive is a positive. That tells us that our function is concave up there. So that means x equals 3 is a local min. On the other hand, plug in -3, that was your other CP. We'll get a negative, a positive number over a negative number is a negative. That means it's concave down, looks like a frown. It has a CP with a horizontal tangent line, therefore it must be a local max. Right, so the second derivative test is an alternative to the first derivative test. You can do it either way, anytime, it's your choice. Sometimes the instructions will explicitly say use one or the other, so you need to know them, but then you'll probably have a favorite after that point. And they both get you the same information. Okay, so again, another good thing to do would be to graph this original function and check that it does visually check your analysis with calculus. All right.